Thanks for clicking on the video. My name is David. I'm an applications engineer at Capture 3D. Today we're going to discuss a little bit about virtual clamping. What is virtual clamping, you say? Imagine you have to pay $100,000 for a very complex fixture to clamp your part into place. Now, imagine you don't have to pay $100,000 to clamp your part into place. That clamp never needs to be adjusted, doesn't need to be calibrated, never wears out. Because with virtual clamping, you're digitally, mathematically clamping your part into place. Every time, the same way. There's no more error in person-to-person clamping. Stay and watch the whole video, and I'm going to jump on my PC and I'm going to show you exactly what I'm talking about. Before we do that, would you please, wherever you find your like and subscribe button, hit that for me to keep up with the great content that my coworkers and myself are putting out here at Capture 3D on all the great features of ATOS. So we're going to open up our new project. I'm going to come down here, I'm going to open up our project data here, drag and drop our CAD, new part. Now when you drag in CAD and you still want to search around for it, from basic training, if you come down here, there's this little guy called Reset Zoom. A lot of people forget about this, but if you click it, it zips that CAD back into frame for you so you're not searching all over for it. So next, I'm going to come down here. I'm going to bring in our mesh, add that to the part. So since I have CAD and I have mesh, I'm going to give it a pre-alignment. Alright, next I'm going to add our nominal geometries, RPS points and such. Add that to part. And now, the big thing we need to talk about here, I'm going to add, is the deformation model. So we're going to add that to our part. So what is a deformation model? A deformation model is what makes clamping, virtual clamping possible. How is it different than anything else that I've added to this part so far? Glad you asked. So what I'm going to do is I'm going to actually show you here. So when we first look at it, it looks like we've just turned the mesh structure on a mesh. But it differs in that it's uniformed all the way across, and if you look in, like say, a CAD model here, if you look in the information over here, not really much on the way of information, but if we look at the information on, say, the deformation model, ton of information here. So what you actually get is you get volume, mass, density, the Young's modulus and Poisson's ratio. So how do you come by getting this? Well, what happens is you give GOM a volumetric, which means it has a thickness, a volumetric CAD model. GOM then in turn turns that into the deformation model. The deformation model is basically a digital representation of a physical piece of sheet metal. It's what makes virtual clamping possible, because this deformation model will actually bend, flow, have strain just like a real piece of sheet metal would in the real world when you actually go to do your clamping points. So now I'm going to actually show you how that works. So what we're going to do is I'm going to first rename these guys, because that's 1, 2, 3, 4 gets confusing. So I'm going to rename these guys here. So first, let me rename these RPS Z. These are going to be
RPS. Y, this guy down here, is RPS X. So now, what you just seen me do is it's a multiple points here. I highlighted these and I can press rename. And what it allows me to do is rename multiple points, the same name, but then it numbers them for me to keep them in order. That's one way. But if you just have these singles, just a single point here that you want to rename, and you have all these other ones, you just want to highlight this one. Instead of having to come down here and right click, you can use this function here, which it says rename, and then it also gives you the hotkey to do the same thing without having to right click and all that. So when I come up here, I can highlight this, press F2, and just rename it. Clamping point. All right. So now I've got all my points, have names. So what I want to do now is I'm going to give them measuring principles and checks. So I'm going to hit Control right click, brings up our eye inspect window. I'm going to highlight all our Z points and give them a measuring principle of intersection with mesh. And while I'm at it, I'm going to check them in the normal direction. Now our X and our two Y's, if I zoom in here, they're not surface points, they're edge points. So I'm going to give them the measurement principle of touch point edge. And not checking them in the normal direction, I'm going to check them in the trimming direction. So zoom back out here. And now our clamping point, since it's a surface point, I'm going to give it a measurement principle of intersection with mesh, and I'm going to check it in the normal direction. So our deviation, pretty spread out. So now that I have everything here, I'm going to set an RPS. So I'm going to highlight all of these points for my RPS, and then I can bring them all in at once. Change this guy to Z and hit OK. So now I have you see all these guys are 0 except for, holy geez, all of our deviations pushed up in this corner. So basically this represents what this would look like if it were just clamped in the RPS position. Every one of these RPS points are 0. So let's actually see what that actually looks like. So we're going to come down here, make a surface comparison on CAD, hit OK. Ooh, they've changed that a little bit. There we go. So you kind of see what that looks like. Throws all that deviation over here. So now what we need to do is figure out a way to clamp this guy down to even this surface out here. That's where virtual clamping comes in. So now you've always been able to just put a part in RPS, but you've never been able to clamp it in RPS plus other clamps. So basically what we're going to do is we're going to clamp it and add this clamping point to it. So how we do that is if you have GOM Inspect Professional or ATOS Professional, this virtual clamping is an add-on to that software that you would get from GOM. So where it is you go to Operations, Mesh, and right here. This virtual clamping, like I said, it's an add-on and it has two separate functions. The one we're going to do today is by clamping points, but there's also another function that comes with peripheries, which is a pneumatic clamping device that you would also get from GOM, and it actually has the function of gravity compensation, which means that if you had a very flexible part plastics, single part sheet metal. What you would be able to do is inside this pneumatic clamping device, you would lay it flat on a rotation table, and then you would measure it. The software would then perform gravity compensation for the actual bow and bend in the part from gravity. Basically take the gravity out of it, then it would rotate it from that horizontal measuring position into its actual car position or normal position inside of the software, reapply gravity, and then clamp it. Very convoluted, but I'm going to show you some slides that kind of would better explain it than I can right now. But first, we're going to go ahead and I'm going to show you the by clamping points first. So we're going to go by clamping points here. Now, we're going to choose our actual mesh, our deformation model. Then we're going to come down here. We need our holding points, which is going to be our RPS points. I'm going to click this button. Instead of bringing them in one by one, we're just going to actually, since we've already got an active RPS, we're going to click this. And for some reason, it gave me an extra X. I don't need that. Let me go ahead and delete that. Now, since each one of these is only controlling one direction, and it's not like a cylinder that's going to be controlling X, Y, Z, what we need to do, instead of having them in their own respective axis, we're going to change these to normal for the Z, and then trimming for all the edge points. Now that I have changed all of these, we're going to come down here to our clamping points. So I'm going to click our clamping point. I'm going to add it. So now it gives me, okay, point is our clamping point. Observation point. Now, if you actually had a physical clamp and in your CMM you had to have an observation point or a helping point because you were not able to get to that point due to the way the structure of the frame is or something, but you have a point adjacent to that point, that's the XYZ values you would have here. You would use that point as an observation point. Direction, we're going to be in normal. Or you could actually put the individual direction. Movement in plane. Now, why would we want movement in plane, or why would we want to block the movement in plane? Movement in plane means if this is a welded part, it's very rigid, then we want to block it because we don't want that movement because it's welded. Well, allowing movement in plane, since this is not a welded part, we're going to allow the movement in plane. Now I'm going to go down and show you expert parameters. This deviates to 10 iterations. You have iteration tolerance. Once this iterates so many times that it actually falls below your iteration tolerance, that's where it stops. If you wanted it to go all the way down to 0, clamping this point all the way to 0, you would put it down to 0.1. Then your clamping mode, consecutive or simultaneous. You can actually have it clamp in this order right here, or you can have it clamp all at one time. Either way, you'd actually use this clamping mode right here. So now we've got everything filled out. We're going to hit create and close. So you can look down here, it's going to start our first iteration, shows you the current deviation. What it's doing, it's virtually clamping while also making a whole nother CAD model besides your original CAD model. So you can actually see the difference from each one of those after it's been clamped and before it's been clamped. So now we're on our third iteration, we're at 0.5 deviation. It wants to get below 0.1, so it's going to go one more iteration. Yep, there we go. So now it's going to wrap everything up, creating our CAD model comparison for our new mesh that it's creating in the clamped position. And there it is. There is a virtually clamped part. Each one of these are clamped to 0. And that's what our part looks like when it would be clamped. And now, the really cool part, now that with our deformation model, I'm actually going to show you something else. So, when you're clamping and something's really tough, that's a human feedback. When it takes a little pressure to push something down, you know the metal or the plastic is not correct. It's warped, something's wrong, and something needs to be addressed. But doing this virtually, you don't get that haptic feedback, that human feedback of actually pushing the clamp down. So what GOM has done is they've actually given this right here. You can actually visualize the clamping force in newtons. So now I know this clamp actually took 19 newtons to push that into place, to get that into shape. So once these numbers start to climb, you can actually put tolerances on them. If it starts getting out of whack, you actually can see the force it took to clamp, and then in turn relay that to your engineers and things that, hey, this is a little out of whack, you might want to check your process. So now, that is virtual clamping by clamping point. Hope you guys enjoyed it. Stick around, I'm going to explain a little bit more about the other virtual clamping, gravity compensation. So virtual clamping, the current state of the art is the qualification of the parts in fixtures. So the part qualification procedure goes like this. The tool maker is trying to produce a part with as little warpage as possible, meaning just coming out of the press, the die, stamp, however you want to say it. Warpage within an acceptable range or force, meaning like Newton clamping force, is uncritical and is eliminated during subsequent assemblies like welding, brazing. It's pulled into position. But the part manufacturer only wants to qualify his or her parts, not the fixture. The problem with fixtures is the construction, production, calibration, and storage. You got to take all these in consideration, and the costs are really high. The high investment of time comes in with multiple measuring cycles for different clamping situations and iterative adjustments of the clamping points. If they're bent, you have to fix them. Complex change management. Whenever someone's trying to change a part, a new revision level of a part comes out, well, now you have to change the clamp to meet that new iteration of that part and also modify the CAD model. Limited accuracy. It's non-perfect supporting points, limited repeatability. You have person-to-person interference, different clamping orders, unidentified friction at the clamping points. Then you have limited accessibility, the hidden measuring points, because it's now covered by a clamp, and the actual direct clamping point where the clamp is actually touching the part most of the time is usually a datum, so you have to take an adjacent point to the side of that datum and not that datum. So kind of show you the workflow here. The workflow is just like a normal, you're going to have the CAD model, you scan the part, you get the digitized part, which is the mesh, and then you get your normal CAD comparison, you get the deviation at the clamp points. This is what the tool maker wants to see to correct his dies. But then you add in the deformation model. Well, with the deformation model, we then can do virtual clamping. We create the displacement field, do another CAD model comparison, and this is the assembled and final quality version of that part. But we never had to do anything else. We just scanned the part one time, We can give the tool maker what he needs and give final quality what they need, all with one part. So the deformation model, I talked a little bit about it in the demo. It's basically the computational basis for deformations and forces. It's what allows us to bend and flex in a virtual world like a real part would. Describes the deformation behavior during clamping and under the influences of gravity. The properties are the discretized geometry, Young's modulus, Poisson's ratio, and density. It requires a volumetric CAD model, also same for sheet metal, a CAD model that actually has a thickness. Once you give that to GOM, you get back your deformation model. So here you can actually see the same part we did in the demo. You see the virtual clamping side and the actual mechanical clamping side, and you see they're almost perfectly identical, except with virtual clamping you get a number of how hard it was to clamp instead of a worker saying, hey, that's a little tough to push down there. And you can record that, track that, and actually it gives you kind of a little alarm bell function as to how the part's riding out. And here we get into more of the non-rigid and not in a relaxed or in a relaxed position using the pneumatic clamping device that we have. So the pneumatic clamping device is extremely flexible holders with 3 pneumatic suction elements. There's a smart valve for the complete free state. So what that smart valve does is actually once you set the part down, it clamps, then individually puffs air out, relaxes, and clamps back in sequential order, allowing it to be in a perfect free state. It has photogrammetric position identification for each one of the clamps, so the software can identify where they are in space. And then you have very good accessibility for all your measurements, so there's no more blocking of points, reliable mounting, a large variety of part possibilities because these are maneuverable and also relocatable around the measuring plate. So the functions of gravity compensation: measurements in an unclamped state, location of the support points, your pneumatic clamping device, the directions of gravity and your deformation model. The results you get are gravity compensation, measuring in a weightless state. So why would you want to measure in a weightless state? Well, if you're measuring in a, say, what we actually have in the picture is a window frame. Well, a window frame is not supposed to be measured laying down flat because it's being bowed, it's flexible. It needs to be propped up in car position and just past a 90-degree position to basically look like it is supposed to be looked at in an assembled position, also clamped. So how does the software take into account all of this? So first, you put your part in the pneumatic clamping device, laying down horizontal. It's measured in the unclamped state horizontally. The software then takes gravity compensation, makes it weightless. Well, from there, it rotates it up into car position, then re-adds gravity, then virtually clamps it after re-adding gravity and gives it the assembled location fully clamped with also gravity. But you measured it completely horizontal and with a bow in it due to gravity. So this is kind of what that process looks like. You have the window frame laying down, unclamped, held in 3-point position. The computer then takes it to a weightless state. That weightless state is then transferred up into car position in an unclamped state, and gravity is re-added. and then virtually clamped into position in the final assembly location. And this is integrated into scanning template concepts of the GOM software. So once you would basically do this one time, this would become a template function to where you wouldn't have to keep doing these steps over and over again. So the process capability of analysis. Part is mounted, measured, unmounted several times using the universal pneumatic device. So data processing involved in this particular study here: remove gravity, add gravity in the mounting position, and then virtually clamping. Deviations, variations at the holding and clamping points are 0. The variation of surface measurement is low, less than 50 microns, compared to corresponding mechanical fixtures, which vary. So basically here you have the mechanical fixturing with physical clamping and the pneumatic device with virtual clamping, identical results within the scattering of mechanical processes. The 2019 software support, basically that's where they brought in virtual clamping. You can actually, it has to be uniformed material. It can't be multi-layered, welded, different materials. So uniform materials, uniform material properties, elastic deformation behaviors. Single parts, no assemblies, has to be smaller than 2 meters. So here you see a B pillar for a car, cell phone case, fender, window frame. So what we have is the ability to cut costs dramatically, save time, save space, save the backs of reloading, unloading fixturing, and have all this done inside the software. Now I know that was a lot of information in a very short period of time. But if this presentation has piqued your interest about virtual clamping, reach out to your Capture 3D sales representative for more information and to schedule a demo. And also, would you please click like and subscribe to get all this great content that me and my coworkers are making to help you and your company succeed. Thank you for watching this video, and have an awesome evening, morning, 2 a.m., whenever you're watching this video. Have a good one. Bye.